we are going to explore inverse trigonometric functions by reviewing inverse functions from college algebra. This is a review of some college algebra that you've done before, but it's a necessary review. It's nice to see it with fresher eyes and also be able to tie in what you learned about inverse functions and just inverses in general to trigonometric inverses. Now, it's going to be somewhat of a hard shift from graphing all of this time to getting into something like this, but you will see near the end of this video why this section is lumped in with the graphing sections of sine, cosine, tangent, and all of their reciprocal functions. So let's begin by doing just some simple work with exploring trigonometric functions by looking at inverses. Now, I will give you a warning, and I will also just let you know that I can make this mistake as easy as anyone else. The warning is the process of taking an inverse is sometimes called as an opposite or reciprocal. Well, these terms definitely do not work in these cases. Now, again, be very careful when you mean opposite. You're generally saying like 5 and -5. Those are opposites because they have an opposite positivity or negativity. Reciprocal is kind of like saying 5 and 1/5. Those are reciprocal numbers. But we're going to talk specifically about inverses. So if you look at these four examples, we've had inverse operations before, and it was pretty much the backbone of your algebra classes. So for example, if we were to try to solve for x here, we would have to get rid of this -5 to get the x and isolate it. So we'd add 5 to both sides. This is an inverse operation. And then what we have here is a lot of students call cancellation. This is one I'm kind of okay with calling cancellation because it actually makes it 0. But I will probably stick to the more accurate term simplification because 5 and -5 make 0. Then we divide both sides by 2 and x, then simplify. X is all by itself because 2 divided by 2 simplifies. This is why I hate the word cancel, because 2 divided by 2 isn't 0. A lot of people associate canceling with make 0, and 0 divided by x would be incorrect. So here x is equal to 6. In this example, we saw two versions of inverse operations: the inverse operation of subtraction and the inverse operation of multiplication. Here, the inverse operation of addition is subtraction, so these simplify. So I've got x cubed is equal to 3, and then I would do the inverse operation of dividing by 3 and multiply by 3. So x is equal to 9. Okay, so here we have another two examples of inverse operations. Here we have the example of the inverse of addition and the inverse of division. Now we've taken inverse operations here because we have to get rid of the square, so what we'll do is take the square root of both sides, and here we have x is equal to plus or minus 3. So the inverse of squaring is square rooting. And here we will square both sides to get rid of the root, and we chose squaring because this was a root 2. We don't usually put the 2 in the corner of this square root, but that's how we have the match here, and x is equal to 81. So in these last two examples, we saw that the inverse operation of rooting was squaring and square rooting was rooting. Okay, so why do we need inverse operations? Well, we need inverse operations to solve for x by undoing, emphasis added there to the word undo, undoing operations. So let's just fill out this chart and kind of put things back in perspective. Now what's important about this chart is that it seems pretty obvious that the inverse of addition is subtraction. But what do you get when you take an inverse of an addition and a subtraction number? Well, you get 0, because you have like maybe 5 minus 5, you get 0, or -6 plus 6, you get 0. And the inverse of subtraction is addition. and you also get 0. I want to highlight this because you don't always get 0, and that kind of makes a very important statement as we get closer to an actual inverse function. Multiplication. The inverse of multiplication is division. And what you get is 1. You don't get 0, because 5 divided by 5 is 1, or even negative 6 divided by negative 6 is 1. And the inverse operation of multiplication or division is multiplication. Oh, there we go. And you get it 1 as well. Now, squaring a number, or the nth power, what you'd have to do is take the nth root. So, of course, with squaring, this is a square root, but if you cubed, you would use a cube root. And this would give you x. So here we're getting into some situations where you're not seeing just a single easy number here. And obviously the square root, or the nth root, what you would do is take it to the nth power. So if you have a cube root, you take it to the third power, and that would give you x. So what we've seen now is we've seen that in some situations you could say cancel because it does make 0, and in other situations it makes 1. But in other situations you can see that we just get x, what was the thing that was inside that root. So let's talk about an inverse of a function. Now we're going to dive deep into this because there's many ways to find inverses of a function, but the way I like to do it is I like to say, if I have an equation y equals 2x minus 4, the way to find the inverse function is to switch the x and the y position. And you may remember this from doing this in college algebra. This would be especially important if you were ever in the logarithmic section of your college algebra class, because defining logarithms and exponents as inverses of each other was using this technique. Alright, so now let's solve for y to see what the new inverse equation is. So I'm going to add 4 to both sides using this inverse operation. That simplifies, so x plus 4 is equal to 2y. Okay, then I'm going to subtract, or I'm going to divide by 2 on both sides, and I like to divide the 2 by every single term. So that when I have 1/2 x, I just, instead of writing it x over 2, I wrote it as 1/2 so I could better see slope, plus 2 is equal to y. So this is my equation. And instead of writing it as y, I can write it as the inverse of x. So these two things are the same because this y equals equation is the inverse of my original f of x. So my inverse equation is 1/2 x plus 2. Now I want to do a couple things here. I want to first of all graph this in green. I'm going to graph that in green. So I'm going to put my y-axis here at -4 because that's my y-intercept there. I'm going to go up 2 over 1, because my slope is 2 over 1, up 2 over 1, and finally up 2 over 1. I normally don't plot this many dots, but I thought it'd be nice to plot all the dots because of what I'm going to do in my end part of this page. Now I'm going to do this line here in blue. Okay, so I'm going to start at 2. That's the y-intercept there. I'm going to move up 1 over 2, up 1 over 2. So these do share the dot. And because I have some room to the left here, I'm going to make this a double negative and go down 1, left 2, down 1, left 2. So again, I don't usually put in all the dots. I usually just put in a few dots and connect the dots. But here's what I want to do in my last example. I want to plot these green dots and plot these blue dots on this table. So this is going to be my f of x table for my x and y, and this is going to be my inverse table for my x and y. And I want you to see what you see and see if, like, why did I do this, right? So the first thing I plotted down here was 0 on my x and 4 on my y, so 0, 4. Sorry, -4. And then I went from there to 1, negative 2, and then there to 2, 0, and then finally to, well, not finally, 3 to 2, and then I went 4 and 4. Okay. Now I'm going to do that with the blue dots. I'm going to check those out. So my first dot, I'm going to go all the way. Let's see here. Where should I go? Well, maybe I should go all the way to the left here, which is my first dot at negative 4, 0. Negative 4, 0. Looking at the green dot over there too at the same time. Okay, and my next dot was going to be negative 2, 1. Negative 2, 1. Okay, then the next dot's going to be 0, 2. Oh, interesting, right? Is the next dot 2, 3, and 4, 4? What do you notice between these dots over here and these dots over here? Well, they're just x and y switched, right? And that literally is the beautiful property of these inverse functions. They're literally the x's and y switched. And you probably haven't done this since college algebra. And I'm telling you, you did, because this is probably how you graphed a logarithm. You probably graphed it by graphing the exponential, and then you graph the logarithm by switching the x and y positions, because exponentials and logarithms have this cool property. And I'll just kind of review exponentials and logarithms right here. So this gray line is an exponential, and then this red line is going to be the logarithm. And you'll notice that there will be this cool x equals y line. Figuring out a new color here. There's an x equals y line, which is not drawn to scale here. But that x equals y line, which I can draw very easily here, is kind of like the line of symmetry. And by I say kind of, I mean it is the line of symmetry. A inverse, and again, you may not have touched upon this unless you've had a pretty good geometry teacher. The inverse is always going to be a symmetric line to this y equals x line. Okay, so we've done that. That seems like a pretty good start. But let's now really bring it home by actually getting into inverse functions. Because what we've done is, I mean, we've done this linear inverse function, but we got to somehow bridge this to the trigonometry inverse function, and we'll do so on the next page. So we are going to continue from the previous page by looking at this function here. So we have our f of x, and then now we have our inverse of x, or f of the inverse function, excuse me, and the inverse function is 1/2 x plus 2, and the original function is 2x minus 4. And we did all that cool stuff on the previous page, just so you're not confused about where this all came from. Now, what I'm going to do is I'm going to highlight this in green, and I'm going to highlight this in blue. And why that's important is because we're going to do something that you did in college algebra called the composition of a function, which means we plug one function into the other function and then simplify it. So what we're going to do is we're going to plug the green function into the blue function. So the blue function is 1/2. This is the inverse of it, inverse function here. This is 1/2. And now the x is going to get a little bit of space to fit the green function in there, plus 2. So again, this is a review of composition of functions. So now I'm going to plug in my 2x minus 4. Okay, so now I'm going to do the simplification work. I'm going to distribute here. So this gives me just x, because 1/2 times 2 is just x. 1/2 times negative 4 gives me just a minus 2, and then plus 2, and negative 2 plus 2, or minus 2 plus 2 is just x. So this answer is x. So the inverse of a function gives you just x, kind of like when we squared a square root, or we took the square root of a square. Let's test this out for the next function. I'm going to start off by plugging the inverse into the actual function. So let's go write my actual function to Now instead of an x, I'm going to put a big wide parenthesis so I can fit the blue in there. And this is going to be then 2x minus 4. And instead of my x, I'm going to write the blue equation, 1/2 x plus 2. Okay, do a little distribution here and here. And this gives me 1/2, or 2 times 1/2, again, is just 1. And that gives me x. So 1 or 2 over 2, x is just 1x, which we would just write as x. And 2 times 2 makes 4. 4 minus 4 is just x. So the function and its inverse make x. Therefore, the inverse of a function is called the inverse function and gives you x. And why do we need inverse functions, especially in this class? Why do we need inverse trig functions? To undo, emphasis added, the function and solve. Now you'll note that I'm not telling you what we're solving for. I think I want to get into those problems and then kind of like reveal what that's talking about, because you know, it could be an x, it could be a theta, but we are using these inverse functions to basically this word, to cancel out the trig. I hated using that word cancel, but you know, it's been ingrained in your brain and it's just going to feel better. Now, I promised at the end of this video, this is a huge transition. We have just spent like days, maybe up to 2 weeks, graphing and just graphing and graphing and graphing. So why do we have this inverse section here in the graphing section? And it all comes down to maybe the visual perspective here I want to show you. So let's just do a sine wave. And a sine wave is medium, high, medium, low, medium. And this sine wave is 1 period from here to 2 pi. But unlike the graphing that I've normally done, I do want to go into the third and fourth quadrant here. Or sorry, third and second quadrant. So we'll just go medium, high, medium, low, medium. And you can see that I've chosen that my height of this is going to be 1 and -1. And my width is going to be -2 pi over here. So my domain is going to be all real numbers, or from -infinity to infinity, and my range is going to be hard brackets -1 to 1, because this is my y maximum and minimum, and my x's go on for infinity and beyond. Now, the reason why I'm doing this is because I want you to see the inverse function. And I am going to take some of the toil out of doing this problem and telling you that we could plot all these points on a table, we could flip the x's and y's around, and then we could graph it on the table, but from the table. So I've done kind of the hard work for you. So what I'd like you to do is I'd like you to start at the origin, just because this graph starts at the origin. And I want you to go to this point here, 2 tick marks over, 1 tick mark up, then just 2 tick marks up from the origin, then 2 tick marks over to the left, and 3 tick marks up, and then back here. This is the inverse sine wave. What we've done is we flipped our x and y axis, so now our x is up here at our x is now our y at 2 pi, and this is going to be down here at -2 pi. So from the origin, go down 1, left 2, down 2 from the origin, then down 2, right 1, and then down 4 from the origin. And this continues your inverse sine wave. So the reason why they're putting this here is so you can see the graphical representation, and it's all about the domain and range, because this does go infinitely on my range now. You can see that this wave would continue on, snaking up or down depending on your perspective, so the range is now all real numbers, or as I'm using these interval notation, from -infinity to infinity. But my domain is now locked between my -1 here and my +1 here. So now my domain, just like flipping the x and y tables, is now flipped here. And we're going to do this for cosine and tangent, and show you some of the subtle differences we'll have to think about when we do these two. And this will end our first video. And yeah, this first video was pretty lengthy, but it had to cover all of the basics about an inverse function so you can kind of see this put together. So let's go to cosine. Cosine is going to be, let's start with the y-intercept there. High, medium, low, medium, high, like that. And this makes our 1 period going from here to 2 pi. And let's go actually in this direction. High, medium, low, medium, high. Feels weird being in that second and third quadrant. Negative 2 pi. And we're going from 1 to negative 1. So we're going to flip the x's and y's around, and I've done that work for you. So now what you get to do is kind of reap the benefits of me working ahead. And we should also fill this out before we get that too far ahead. Our domain is all real numbers, and our range goes from negative 1 to 1 inclusively. Okay, so now what we do is we're going to do our cosine here, and our cosine is going to be, instead of high, medium, low, medium, high, we're going to start. I want you to put your first dot 2 tick marks to the right of the origin. Then I need you to go, let's see, just making sure I got everything right. 1 tick mark up, and then 2 ticks from the origin up and 2 left. From the origin, 3 up, and then 4 up, and then 2 over. And this is your inverse cosine graph. And we'll just copy that down below. From the origin, 1 down. From the origin, 1 down, or 2 down, 2 to the left. And then 3 down, and then 4 down, 2 to the right. Look at that. Pretty, isn't it? So the range is now going to be from negative 1 to 1. Or sorry, the domain is going to be negative 1 to 1 inclusively. So we're including the 1 and negative 1 because we can actually touch those numbers as we do our cosine inverse. And our range is going to be all real numbers, or an interval notation like this. Okay, time for the tangent, the most tricky one around. Tangent has a much shorter domain. Or sorry, not yeah, let me see, that's domain. Yeah, we'll talk about domain in that way too. So I say shorter just because it does have asymptote lines, and those asymptote lines are here. Okay, this is an asymptote line. And that asymptote line is at pi over 2. All right, so let's now get this 1 period pictured. Now, what you might be thinking is like, gosh, how can we fit 1 period between here and here? Well, actually, unlike the previous graphs where I wrote 2 periods, I'm going to do just 1 period, and I'm going to do that 1 period starting at the origin, and at pi over 4, which is halfway between pi over 2 and the origin, I'm going to have this as 1. Okay, so what you're looking at is you're looking at a half period here. That means the other half would be down here. Okay, that would be down here at negative 1. See, that's negative 1. This is positive 1. Oops, I'll get rid of that glitch in just a second here. There we go. And then we get into another asymptote line here at negative pi over 2. So our domain and range, we've got a full period here. But our domain and range are going to be a little bit different. Our range is nice because our range goes from negative infinity to infinity. Okay, that's pretty nice. But now let's check out our domain. Our domain does not go past these asymptote lines. So these are parentheses, not brackets. So this goes from negative pi over 2 to pi over 2 exclusively, which means we don't actually touch these two parts. So again, I've done the hard work for you, so let's do this inverse where we flip the x's and y's. So my y is now pi over 2 and negative pi over 2, which are now asymptote lines. These horizontal lines are now asymptotes. Now lucky for you, we don't have to graph these, but we do in the next series of videos do have to process them. And here we have an origin, right? Because this is where we started over here. Now, if this is 1, then this is going to be the dot here, and this is going to curve in this direction, like so. And this is going to be -1, so 2 tick marks away at -π/4. We're going to be here, and this is going to curve like this. All right, so now my domain is going to be all real numbers, because you can see that this is going to go forever and ever and ever in both directions. But the range is now restricted between π/2, -π/2, and π/2 exclusively. We're not actually going to have those in there. Well, now you can see why all of this gets connected together. And thank you for watching, because this has been a great review, but I think now the next series of videos that kind of talk about all of our work with inverse functions in trigonometry is going to go much more smoothly. All right, thank you for watching.